All right. So today we've got some things to talk about that are ancillary to what we need to learn about acids and bases. And the first one we're going to start with is molarity. Molarity is a concept in chemistry that we have used before. We just didn't define it. We didn't really talk about it at the time, but we have seen this before. When we did the reaction rate lab, where we added, I think we were adding, it was either zinc or magnesium strips to test tubes, and we had two different concentrations of HCl. We had a 0.1 molar and a 1.0 molar solution. One was a greater concentration, and we checked what the reaction rate looked like and whatever. So we've seen this before, but we've never really defined it. So molarity, put as simply as I can, is moles of something per liter high. Okay. Molarity is moles per liter. Now again, here is the specter of moles being used to define something. And we all in this room know how to calculate moles of something. And liters is just the measurement of volume. So we're going to do a little exercise today. Who here knows how to make Kool-Aid? The old-fashioned way. How do we make Kool-Aid? Easy, Henry. All right. Yeah? Okay. Half a bag of sugar. Okay, so I'm almost certain if we were to check the actual printed recipe, half a bag of sugar is not what the recipe would say. Now, I, back in the 1800s, was also a kid once, and I also put extra sugar in the Kool-Aid when I was allowed to make Kool-Aid. But for the sake of science, today, we are going to follow the correct formula for Kool-Aid. To make Kool-Aid, you need these two ingredients. 1.9 liters of water, that's your 2 quarts, give or take in freedom units, and 200 grams of sugar is the official recipe. Calculate the molarity of your Kool-Aid as it concerns sugar and water. Calculate the molarity of the sugar in the water for Kool-Aid. I got the formula in the top right up there. See where it says molarity equals moles per liter. So calculate the molarity here. You have in your toolkit the tools to be able to calculate this. You need moles and you need volume, which is liters. So you have liters already there. How would we calculate the moles of 200 grams of sugar? Yes? T-chart, yes. You will need a T-chart, indeed. Indeed. The key is, what do you put in that T-chart, Henry?
200 grams of sugar.
Okay.
And then you bring down the grams.
Yes.
And then you got to find the molar mass of glucose or sucrose.
The molar mass of, it's like maltose or something, it's like a table sugar is what this is, but.
Okay. Yeah, and then you got to find the molar mass of that.
Okay, how do you find the molar mass of this?
Whatever 12 carbons is, 22 hydrogen.
Yes, I'll wait while you do that on your thing, Henry. You know how to do this. Yes. So calculate the molarity of our sugar water solution here per the actual recipe, not the half a bag estimate.
Not half a bag, not right. Yeah. How many grams? 342.
Ben, you figured it out? I don't see anything written down here.
And then what is? Yeah. 200.
What is our molarity? Anybody got an answer yet? What'd you get? Yes. Did you get an answer? The molarity. That's the molar mass, yes. But the molarity.
It'd be moles per liter.
No. Let me see. Where's your work?
Well, I've got like 0.8 something moles divided that 1.9 liters of water.
0.8 moles. That can't be right. That sounds high.
Two.
That's right. But you're not done. Right? Yes. But you don't have 1 liter. You have. Yes. So this then divided by the 1.9 will give you your answer. All right, so let's walk through this. So if we have 200 grams of sugar, David, bruh.
David just broke the
Luckily for David, we have hundreds of those things. So we have a solution of sugar and water, a 0.305 molar sugar solution. That means the concentration of sugar in our Kool-Aid per the recipe is this. Now again, I will admit you guys probably put extra in there, but whatever. This is what it's supposed to be. Okay? So, could we do the same thing Could we do the same thing for this? What is your guess? More or less sugary? Mountain Dew versus Kool-Aid. You're saying the Mountain Dew is more? Now that you know how to calculate it, calculate the molarity of sugar in Mountain Dew. And this is right from the side of the can is where I'm getting this data. Ben. Same sugar, yeah, use the same sugar. Yes. Use the same sugar molecule as we used for the last one. Well, it's moles per liter, so. And our guess is Mountain Dew is more sugary than Kool-Aid? That's our guess? Anybody get an answer yet?
Yeah. 0.27.
So how many moles of sugar are in a Mountain Dew?
0.37.
And then how many liters is 355 milliliters. Are we sure about this? Are we sure about this? Yeah. Yeah. That didn't pass the smell test. What did you get, Miranda? 0.13. Oh, the moles. We're doing the moles first. So now we can do the thing. So now moles per liter, 0.13 divided by 0.355 equals 0.37 molarity. So which solution was more sugary? Which has a higher concentration of sugar in it? Mountain Dew, right? 0.37, the first one was, what was it, 0.30 or something, Kool-Aid? Right? So that's what we're talking about here. We're talking about particles of something in solution. Now, you guys didn't see it, but every time we did some kind of lab with the blue solution, remember the laser beams and the blue test tube solution? That was just copper sulfate. And he's here today. David is, when not breaking glassware, he is mixing up all of those different solutions that we've done for labs, and he has to do the same thing. And typically, what are those, 0.1 molar solutions of all those different things? Yeah, so when he's making solutions for all the test tubes, all the droppers that we've used, all the different solutions throughout the year, he has to make each of those solutions out of some kind of salt, typically, that we have in jars in the other room. So he adds some certain amount of those chemicals to some amount of water to make up those solutions. So that we know, instead of just, yeah, add a little bit of this and add a little bit of that, it's very specific. We want to know what the concentration is. If you took a sip of Kool-Aid and the molarity of the sugar was 0.1, would it taste right? I'm guessing not. Right? It would not be sweet enough. If we followed Henry's recipe, the molarity of probably 9 molarity sugar water would be way too sugary. It would probably pour out like maple syrup instead of Kool-Aid. Just call it delicious, I guess. Call it delicious. Wouldn't even dissolve. You had that thin layer of sugar at the bottom of the thing, no matter what you did. Saturated solution. All right, so let's go back to acids and bases. So there is a reason that I've been talking about molarity today after our introduction to acids and bases yesterday. Inside of a solution of water, here's our beaker of water. God, that looks awful. How do you make the, isn't there a bunch of image? You know what, I'll figure it out later. So here's our water. Yesterday, when we did the pH strips, what did you find was the pH of water? Just the regular water. 7. It's right at 7. And yesterday we just discussed this. We didn't get much further than that, but what did we discuss is a neutral solution, not acidic and not basic. 7. So water is neutral. Inside of water, generally, there's a bunch of these. Would we agree? Yes. It's a very scientifically drawn picture here. So in regular water, sometimes, because of collisions, sometimes because of chance, sometimes these split up into their ions. break up this one too. Guys, stay with me here for a couple more minutes. So sometimes that water breaks up into two different ions, an H plus ion and an OH minus ion. But now because we started with just plain water, the numbers of those are always going to be the same. For however many H pluses we have, we're going to have an equal number of OH minuses. And that's why water is going to stay neutral. Okay? If we add something like HCl, okay, this is hydrochloric acid, if you remember, HCl. If we add some of this, and this HCl in water, when it dissolves, is going to kind of split apart into these two ions, what will be the impact on the number of H pluses and OH minuses in this water? It would be uneven. Why do you say uneven? Yeah, so if we add some HCl's in here, we're going to add some extras of these, are we not? And now, what is the balance of H pluses to OH minuses? More H pluses. That is an acid. An acid is a solution in which you have more of the H pluses than OH minuses. At its most basic level, that's what we're talking about. And if we're going to talk about how many of them, right, we're going to use molarity to figure that out, right? We're going to talk about the number of moles of something in solution, which is to say the number of actual numbers of things, right? Remember, moles is just a number. So when we're talking about molarity, that's what we mean. We mean the concentration of H plus versus OH minus. The more H plus, the less OH minus, the more acidic something is. This would be an acid. Right? Everybody with me so far? Now let's reverse this. What if we were to add something like sodium hydroxide to this? What do you think would happen now? Yeah, what are we going to add to this solution? OHs. So now, what is the ratio, boys? So now what is the ratio of H pluses to OH minuses? What? Now there's more OHs, right? We just added in a bunch more OHs. When this separates out, the OH minuses, the hydroxides, are now going to outnumber the H pluses. And this then would be a base. So that is the fundamental difference between acids and bases. It is this ratio between H pluses and OH minuses. This is how we define acids and bases. Yes, sir.
It doesn't like deal with oxygen or hydrogen.
Then we're not talking about acids and bases. Somebody said yesterday we were talking about, what was it, acetone. That's not how this works. We're talking about H pluses and OH minuses and all of the different compounds that will make this happen. Right? Sodium hydroxide is a clear one, right? I don't know I'd have to look up the formula for a bunch of other bases, but that's what's happening inside them. Now that said, other compounds, when mixed with water, can get you this kind of thing. Can influence the number of H pluses and OH minuses. But this, at its most fundamental level, is kind of how this all comes together. Okay? So there is a formula now hang tight with me here. Square brackets is a shortcut for molarity. So what am I saying in this formula? I know it looks terrifying. And it'll get worse tomorrow when we do pH. It's a W. K of water is just a constant. But when we multiply the molarity of the H plus and the molarity of the OH minus in regular deionized water, if you multiply the numbers of those things together, you get this 1.0 times 10 to the negative 14th. Is this a big number or a small number? Small number. Okay? These are generally small numbers that we're talking about. It does not take a lot of H pluses and OH minuses to make up acids and bases. So we're working with generally smaller numbers here. Okay, but the way this works, you multiply these two things together, the molarity of each together, and you end up with 1.0 times 10 to the negative 14th. Okay? So let's try an example to calculate molarity. Actually, let me hand out a worksheet. David, where's my worksheets? Already in the thing. Now the front side of this looks terrifying. Just hold tight. There's a lot of delicious math involved with acids and bases. And most of that is described on the front page of this, but it will all look like gobbledygook at first. Flip over to the back of this at the top. Now, problem set 1 includes calculating molarity of H plus or molarity of OH minus given each of these numbers. So the first one in problem 1, calculate the H plus of a solution whose OH minus molarity is 1 times 10 to the negative 5th. So how would we solve this problem? We simply substitute this in to this formula. In fact, if I was you, I would write this formula right above problems number 1. I would write this. Yes, on the back and the top. I would write this right above the back on the top line. Molarity of H plus times molarity of OH minus equals 1 times 10 to the negative 14th. And so to solve question 1, I just substitute in the OH minus number of 1 times 10 to the negative 5th. H plus times. How would I solve this problem? Just algebra. How do I solve this? Yeah, divide by 1 times 10 to the negative 5th. Those of you math whizzes at home are going to know how to solve this without hitting your calculator. Now, let's go full circle. if I know my H plus concentration is this, and my OH minus concentration is this, do I have an acidic solution or a basic solution? Which of those two numbers is bigger? The OH minus. So how would we characterize this particular solution? Acidic or basic? Basic. I'll leave you to solve those next three for homework. Tomorrow we'll get into actual pH. We'll hit the log button on your calculator. For those of you that have never done so, it'll be a little bit enlightening. For everybody else, get into your quiz spots. You're going to need a calculator and a